Hi, Math 3. I miss you guys. I think I should be back on Monday. I appreciate your understanding as I'm dealing with this medical issue for my son. I'll probably share more on Monday. So I want to talk about a slightly different type of parametric equation problem. We're going to have a assessment at the end of next week if all goes well. And this will sort of be the last type of thing that we look at. Okay, the last type of problem. So you should have this handout. This should be pretty fast. So we're going to talk about two things, and the big difference with this type of problem is that we're dealing with two different times here. So we have T for the snake, and we have U for the mouse, okay? So hopefully you guys can quickly skim this problem. We have a snake moving with this set of parametric equations, and we have a mouse moving at this set of parametric equations, okay? And what we're going to sort of think about this here is that if you were a predator and you were trying to catch some prey, right, you might not want to start at the same time as the prey. You might want to sort of time your move towards the prey so that you could catch it and sort of meet it at the intersection point at the same time. That's sort of how we're going to structure this particular type of problem here. So first two things that we want to look at, right, we want to look at the speed of the snake, which is simple, right? Each second, how far does the snake go? Right, and that's what we said. Each second, the snake goes 4 to the left and 3 up, right? And I'm just pulling those off of these numbers right here, -4 and 3, right? And so that means that each second it sort of does this. It goes -4 this way and 3 up. So 4 and 3. And so how far did it go? It went 5 because it's a 3, 4, 5 right triangle, right? So the snake speed is 5 meters per second. Similarly, the speed of the mouse, right? The speed of the mouse, we have this imaginary 1 here and we have a 2 here, right? So that should be something like, if we thought about that triangle, right, it would look something like this. We had 1 and a 2, and sort of this question mark right here. So this is going to be right root 1 squared plus 2 squared, or root 5 meters per second. That should be hopefully pretty easy review for us at this point. Okay, so now let's think about where's the snake after 4 seconds. And what I mean by this is where's the snake 4 seconds after it started moving. And the snake was using T, right? So we're going to plug in 4 for T and sort of see where that leads us, right? And so that's going to lead us to x equals -4 times 4 plus 17 should be 1. And y equals, what is this? 3 times 4 minus 9, that should be 3. All right, so the snake is at position 1, 3. We should be pretty happy with that. And what about where the mouse is at this time after 7 seconds? So here we're going to say u is 7. Because remember, the mouse is going to start at a different time. It doesn't necessarily have to start at the same time as the snake. Right, so if we plug in that for u, we're going to get x equals 7 minus 6. That's 1. And y equals 2 times 7 minus 11. That's 14 minus 11. That's 3. So the mouse is at position 1, 3. So what does this mean that we got the same position for each of these guys? The mouse after 7 seconds and the snake after 4 seconds. Right? And so this means that we can say, right, clearly their paths intersect. And I encourage you, after we're done with this video, to pause and sort of try to draw that. Right, that their paths intersect. You could draw their paths on the board maybe. Their paths intersect at 1, 3, because they both get there, right? And since they have different slopes, right, we know their paths must intersect once. So this is their only intersection. Their paths intersect at 1, 3. But their paths, they wouldn't necessarily intersect if they started at the same time, right? If they had the same time. If we use t for both of them, the mouse would get there after 7 seconds, and the snake would get there after 4 seconds. So if we think about the snake, trying to eat the mouse, sorry if this bothers anyone, right? The snake is trying to eat the mouse. The snake would get there too early, and the mouse might sort of see it, right? But if the snake waited for that 3 seconds, right? Because the snake gets there 3 seconds before the mouse. If the snake waited for 3 seconds, maybe it would sort of end up, eating some lunch, right? So what this means is, right, their paths intersect at 1, 3, but not necessarily at the same time. So the question is, how could we make sure they intersect at the same time? So let's show this algebraically. And what I mean by that is let's solve for when they might intersect, not where they might intersect. So the way we're going to do that is we're going to create a new system of equations, going back to our first unit. And if we think about where they intersect, right, we're going to set the x equations equal, and we're going to set the y equations equal. And then that's going to give us a system of equations with two unknowns. And the unknowns aren't going to be x and y. They're actually going to be t and u. Okay, so what that would give us in our system would be that the x's would have to equal each other in terms of where they intersect. And the y's would have to equal each other in terms of where they intersect. And this looks kind of crazy here, right? But you guys could all solve this system. You could solve this however, with whatever method you guys might want. I'm going to clean it up a little before I solve it, sort of get it into a form that we're more used to. So I'm going to have the top one be negative 4t. I'm going to subtract u onto this side, and then I'm going to subtract 17 onto the other side. So it's going to be negative 23. And then I'm going to have 3t. I'm going to subtract 2u. And then I'm going to add 9 to get negative 2, I think. So, again, you guys can take whatever steps you need to solve this system. You can pause me and try to solve it together right now. Sort of see where we get. You could use elimination or substitution. I think I'm going to multiply this top equation by 2. So why don't you pause me and try to do that together. All right, so hopefully you paused me and you maybe you're all just sort of waiting for me to do it. I don't know. But anyway, we're going to get something that looks like this. Sorry, I want to multiply this by negative 2. Negative 2 up here, because that makes everything positive. So anyway, we're going to add these two things together, and we're going to get 11t plus 0u equals 44, or t equals 4. And then if we plug that back into either of these equations, I think you'll see, right, if we get negative 4 times 4 minus u equals negative 23, negative 16 minus u equals negative 23, u is going to equal 7. So we're going to get t equals 4 and u equals 7. And that's what I sort of set you up for with c and d up here, right? I said, oh, look, if t is 4 and u is 7, their x's are the same and their y's are the same. And once we find that, right, we could plug in t equals 4 and find out that x, again, equals this value from that equation when t is 4. And y, again, equals this value at that point. So you could again find that x equals 1 and 3. So what this means is, if the snake goes for 4 seconds and the mouse goes for 7, that's these values that we found here, they'll both be at the point 1, 3. And what that meant, again, is that the snake could sort of time it up. If it waited for 3 seconds after the mouse started going, they would arrive at the same time. So I would like you to pause and try to address this silly problem that Mr. Perlis wrote here about a penguin hunting a bald eagle. And this isn't me being, not patriotic. This is me just being sort of a, maybe you're a hockey fan and you'll appreciate the humor. Maybe you're like Haran and you don't care for hockey and you don't care about this. So anyway, the penguin is hunting the bald eagle, just like the snake was hunting the mouse. Sorry for being very bloodthirsty here. And I would like us to try to do a very similar exercise where we sort of want to time it out. Okay, so pause me, go ahead, and try to do this. I guess don't pause me. I think I'm done. I will. I'll have answers posted for this, but I don't think I'm going to walk us through this. So, I hope this made some sense. Once you sort of address this problem and go over it together, there's sort of two more exercises, a similar one about driving from the spiral, and then this one's a throwback. We'll see, but that's kind of where we could go with parametric equations if we want to, maybe on like a bonus or something. So I hope you enjoy the penguin problem.